All right, so welcome back, everybody. So in this session, let's take a look at the numbers system, okay? This is so important that we need to discuss about it because we human beings, we have a number system that we use. The computer have a number system that we use. Even in the computer too, there are other number system that can also be used, the octal, the hexadecimal. Okay, so let's take a look at this. See also how we can also make some conversions. This might look so trivial, but it is not. You really need to understand everything I'm going to be teaching you in this session. Okay. So basically, we'll just be doing it's like a reminder. This session is basically like a reminder. All right, because we already know the decimal number system, the one that has the base 10. So this is the one we regularly use as human beings. We use digits from 0 to 9. Okay, so 0 to 9, we count from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we come back. We now count 1, 0, 1, 2, 1, 3, 1, 4, 1, 5, 1, 9. We come back 2, 0, 2, 1, 2, 2, 2, 3. We come back 3, 1, 3, like that. Okay, so this is the decimal number system. It uses only 10 digits, 0 through 9. And this is the one we human beings use. So on your keyboard, or when you're writing anything, it is this digit that you actually understand. You don't understand the binary, you don't understand the octal, you don't understand the hexadecimal. So this is the one we use. And it is mostly used in our daily lives. Okay. So now there's something you also have to pay attention to, positional value. Right. Each digit value depends on its position and is a power of 10. Now, if whether it is the decimal, whether it is binary, whether it's hexadecimal or octal, every digit in a particular figure, in a particular number, actually have what we call positional value. Now, let me show you. I'm going to bring up my board. Let's say we have a number like, okay, we have a number like, what's happening? Okay, so let's say we have a number like 2, 4, 3. Okay. Now each of these digits, they have their positional value. Now the positional value of this 3 is 0. It starts from 0. This is 1 and this is 2. That's the positional value. When we also have something like 3, 8, don't mind this, my 8, 3, 8, 4, 2. All right. The positional value here starts from 0. This is the positional value. 1, 2, and 3. Okay. So this is the positional values. All right. So every digit, whether it is binary, whether it's decimal, whether it is, they all have their positional values. And this is something you really have to pay attention to. Okay. So I go back to my slide. All right, so an example is this. You see this position, this 2, 3, 4 that we have here. If you really want to get the values of all these, we will work with the positional values. And this is something we already know. So if I want to actually go with this 2, 3, 4, this will be equal to, all right, I will say 2 times, all right. Now, because we are working here, the base is 10. So if we'll say 2 times 10, which is the base, all right, raised to power the positional value of this 2, which is 2. All right. Then I will now say plus, all right, I will say 4 times the base, which is 10, raised to power the positional value, which is 1, and then plus 3 times 10, which is the base, raised to power 0. All right. So if you look at this thing now, 2 times 10 raised to power 2 is 100. 2 times 100 is 200. All right. Plus 10 raised to power 1 is 10. 4 times 10 is 40. And then we have 3 times, anything raised to power 0 is 1, if you remember. So 3 times 1 is 3. So everything will now give you 243. All right. So this is how the positional value work. So you can also do the same thing with this one. All right. It will be 3 times 10 raised to the power 3 plus 8 times 10 raised to the power 2 plus 4 times 10 raised to the power 1 plus 2 times 10 raised to the power 0. All right. So this is the positional value, and this is how you actually get the value. So now, that is how we got all this. Okay. So we also have the binary number system, and this is basically what the computer uses, zeros and ones. So in this binary number system, we only have 2 digits. In the decimal, we have 10 digits, 0 through 9. But in the binary, we only have 2 digits, 0 and 1. It can either be 0 or it can either be 1. Okay, it cannot be more than, we don't have 2, we don't have 3. It's only 0 and 1. And the base is 2. All right. So it is used in computers, electronics, and digital systems. So we have to get familiar with this. Okay, we really have to get familiar with this binary number system, the binary. So each binary digit is called a bit. All right. You can see when you have a binary number, all right, each of the binary digits is called a bit. So let me show you. Let me go to my board. I'm basically going to actually I'm actually going to erase. Okay. So I'm going to erase. Don't mind, this is very slow. I think this is the first time I'm using this. So, but don't worry, as I get used to it, I will be faster. So pardon my slow motion. As if I'm acting a movie. All right? See if I'm acting Indian movie. You know, Indian movies are always in slow motion. I don't know why people even watch those kind of movies. For me, it does my brain. I should be watching movies that will make my brain very active. And remember, you know what we do is always active now. So stop watching Indian movies. They'll dull your brain. All right? They dull your brain. Watch active movies, movies that will make your brain very active. Okay? Yeah. So anyways, don't mind me. Do whatever you want to do. All right. So now let me show you. Okay. So I go with this. Now, this is what binary numbers look like. We have 1, we have 0, we have 1, we have another 1. So this is a binary number. All right. This is a binary number, and each digit, each of these, we have 4 digits here, and each digit is called a what? Each digit is called a bit. B-I-T. Okay. Each digit is called a bit. Do you understand? And the base is base 2. The base is 2. And they also have positional values. We have 0, we have 1, we have 2, and we have 3. So if you want to check what is the value of this number 1011, what is the decimal value of it? We actually use the positional value to go. We'll say this is equal to, we say 1 times, this is the first digit, 1 times 2. Remember, the base is 2. 2 raised to power 3, which is the positional value, plus 0 plus 0, all right, times 2 raised to power 2 plus 1 times, sorry, this is plus, okay, 1 times 2 raised to power 1 plus another 1 times 2 raised to power 0. So we will look at it. 2 raised to power 3 is 8. 1 times 8 will give you 8 plus 2 raised to power 2 will give you 4. But 0 times 4 is what? 0. All right? Then plus 2 raised to power 1 will give you 2. 1 times 2 will give you 2. Then plus 2 raised to power 0 is 1. 1 times 1 will give you 1. So in total, we are going to have 8 plus 0, which is 8, plus 2, which is 10 plus 1. So this is equal to 11. So now this is 11 in base 10. Okay, sorry, let me erase this. All right. So this is 11 in base 10. But this one is 1011 in base 2. So this is how we have converted, although we will be talking about conversion from binary to decimal, but this is it. So this value here is equal to 11 in our own natural binary, our own natural number system. Okay, so now we use these things in electronics, computers. Okay, basically that's what we said that your computer understands zeros and ones. And remember how we got to these zeros and ones. They are the electrons. All right. Presence of an electric current in a transistor is 1. Absence of an electric current is 0. Remember the first few sessions we talked about. So when you have 1011, all right, this is how you work it out, and you're actually going to get 11. All right. So this is the binary number system. We also have the octal number system. The base is 8. It has 8 digits. Base 10 has 10 digits. Base 2 have 2 digits. Base 8 have 8 digits. So digits are from 0 to 7, and the base is 8. So they are shorter form of binary. So it uses 3-bit groupings. Okay. So when we have something, it is useful in memory addressing. You know, don't worry, very soon when you start programming, when you actually our memory system, the addressing is used, they use octal number system. Okay, that is why you need to understand this. Don't take it trivial. No, it is not. Okay, so because there are certain things when you want to see the address of a memory, all right, you'll be like, what's the meaning of this? You can have every memory have an address. All right, our memory locations have an address, just like your house have an address. Okay, our memory locations, your memory in your computer, they all have addresses that we can address, and we can search for that location and get the value in it. So the octal number system is useful in memory addressing and in Unix and Linux systems. Okay, so example is this 5 7. All right, 5 7. Remember, the digits are from 0 to 7. So 5 7, but look at the base is base 8. And if you follow the positional value, 7 is 0, 5 is 1. So you say 5 times 8 raised to power 1 plus 7 times 8 raised to power 0. 5 times 8 is what? 40 plus 40 plus 8 raised to power 0 is 1. 7 times 1 is 1. So 40 plus 7 will give you 47. So 57 in base 8 is actually 47 in base 10. All right. We also have hexadecimal, where we use 0. It is between 0 to 9 and then A to F. All right. So A is 10, A is 10, B is 11, C is 12, D is 13, and so on. Then F is 15. So it has 16 digits. 0 to 9 will give you 10 digits, and A to F will give you extra 6 digits. That's 16 digits, and it is actually in base 16. So it is a compact form of binary. It uses 4-bit groupings. The octal uses 8-bit groupings. Sorry, 3-bit groupings. Okay, so it is common in memory and colors. Most of you that are into graphics design, you would have been seeing, they will tell you the name of a particular color. You see the Hertz value. Sometimes it starts with hash, the hash sign, the hash symbol. Okay, so you are going to see more of this in colors, even in memories too. Okay, so example is this 2F. All right, this is a valid number representation. 2F in base 16. If you convert it using the positional values here, you will have 2 times 16 raised to power 1, which, because the 2 is in positional value of 1, the F is in positional value of 0. So 2 times 16 raised to power 1 plus 15 times 16 raised to power 0. So 2 times 16 will give you 32. 15 times 1, because 16 raised to power 0 is 1. it will give you 47. All right. So you can see that 2F and then 57, they are all equal to 47. All right. So now let's take a look at, let's properly do conversion between number systems. Let's convert between binary and decimal. All right. You have binary, okay. You multiply each bit by powers of 2 from right to left. You have already seen it. So using their positional values. Okay, we have already seen that, and then you sum all values. So that is basically what we did here. This is a binary value, and we now use their positional values to convert them to a decimal value. Okay, so how do you convert from decimal to binary? You divide repeatedly by 2, and you write the remainders in reverse. Now let me show you what I mean. So I'm going to actually erase this. Make it bigger so it will be faster. You can see now I'm getting used to this. All right. Okay, so now I have I want to convert 243. All right. We want to convert it to, this is base 10. We want to convert it to base 2. Okay. Let's convert it to base 2. Base 2. So it says that you have to divide the decimal number repeatedly by 2. So I'm going to say, I'm going to do something like this. I will say this is 243. All right. Then if 2 divides 243, what do we get? If 2 divides 243, what do we get? We will get 242. 242 will be 242 divided by 2, 121. Yes, 121, and we get a remainder of 1, right? So we'll get 121, and we'll have a remainder of 1. Okay, so this is the remainder. All right, so this is the remainder values. We'll now divide again, but you will have to divide the numbers repeatedly by 2. 2 divided 121, we will get what? We will get 60. I hope I'm correct, because 60, yeah, we'll get 60, and we'll have a remainder of 1. We'll divide again. 2 goes 60, we'll get 30, remainder 0. 2, oops, sorry, that's too big. Okay, sorry. So 2 go 30, we'll get 50. All right, and we get remainder 0. 2 go 15, we'll get 7, remainder 1. 2 go 7, we'll get 3, remainder 1. 2 go 3, we'll get 2, remainder 1. 2 go 2, we'll get 2, we'll get 1, remainder 0. Then 2 go 2 go 1, we are going to get 0. All right, remainder 1. Do you understand it? All right, 2 go 1 is 0, remainder 1. So how do you now, you will now have to take this thing from here up. Do you understand? So you will start writing, the first one we have here is this one. This is the first one. So we have 1. The one following it is 0. The one following it, we have triple ones following it. We now have 2 zeros. Then we now have 1, 1. So this is in base 2. So we have converted 243 to base 2. Now, let us cross-check if we really got the answer. But first of all, understand what we did. With the decimal number here, all right, we are going to be dividing it repeatedly by 2, and we will be marking out the remainder. 2 divide 243, we'll get 1. I will get 121, remainder 1. 2 divide 121, we'll get 60, remainder 1. Just like that. That's how we did. And then at the end of the day, you will now take it from bottom up. You see, the first one we took was this one. Then the next one was 0. The next one was 111. The next one was 00 and 11. That's how we get here. So you have to follow the reverse order. So you can actually cross-check this. Let us cross-check this and see if we really got it. So I'm actually going to erase all these things and I will keep the other guy. Okay. I'm going to delete everything. So let us convert this binary back to decimal. Let us see if we really got it. Okay. Okay, so we have this, look at their positional values. This is 0, 1, 2, 3, 4. Oops. This is 5. This is 6. This is 7. And this is 8. So what we have here, we have an 8-bit binary number here. So let us convert it. The first one is 1 times 8 raised to power, 1 times 2. Remember, the base is 2. So 1 times 2 raised to power 8 plus 1, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8. 2 raised to power 8 is already 256. That means we didn't get this already. 2 raised to power 8 is 2. I'm correct. It's 256. So this is we didn't get this. So let's do it. 256, but we converted 243. So this is not correct actually. All right, because 2 raised to power 8 is 256. I believe I am correct. Yes. Okay. So this is not correct from here already. It is more than. So what we're going to do is this. We are going to do it again. All right. There is a mistake somewhere. That is why we needed to cross-check it. 2 raised to power 8 is already 256. So that means our answer is not correct. So let's start afresh again. 243. 243, all right, divided by 2 will give us 1, 2, 1, 2, 1, remainder 1. Okay. 2 go 121 will give us 60, which is 2 times 60 will give us 120, remainder 1. 2 go 60 will give us 30, remainder 0. All right. 2 go 30 will give us 15, remainder 0. 2 go 15 will give us 7, remainder 1. 2 go 7 will give us 3, remainder 1. 2 go 3 will give us 2, remainder 1. Okay. And then 2 go 2 will give us 1, remainder 0. Okay. Then 2 go 1 will give us 2 remainder, go 2 will give us 1, remainder 0. So we have it. Okay. So I think there is a, because 2 raised to power 8, 2 raised to power 8 is 256. Oh, sorry, not 256, it's 126. Oh my goodness. Oh God. You see my error? 2 raised to power 8. Let me use my calculator. So I'm coming. 2 raised to power 8 is 120. Is it 126 or 256? Where's my calculator? Two. It's 256. Okay. So all right, there is an error in this our calculation. There is an error. Okay, but basically you actually divide these things. Okay, so now let's try 1011. Okay, that we did before. Okay, we're going to find out our mistake along the line. So we have 11. All right, let's divide it. Let's convert it to binary. 2 go 11 will give us 5. Remainder 1. 2 go 5 will give us 2. Remainder 1. 2 go 2 will give us 1. Remainder 0. And 2 go 1 will give us 0, remainder 1. And if we go here, we'll now have 1, 0, 1, 1. This is correct. So we say 1 times 2 raised to power 0, 1. I think it's in the positional value that I made that mistake. It's supposed to be 0. The last one should be 7. So we have done what I'm going to correct it. I hope I'm not getting you confused. We have 0, 1, 2, 3. So here we have 2 raised to power 3 plus 0 times 2 raised to power 2 plus 1 times 2 raised to power 1 plus 1. Sorry, this is 1 times 2 raised to power 0. What am I doing? Pardon me. Let me correct it, okay? All right. So I like making my videos very raw. All right. If there's any mistake, you see mistake. I'm a human being, you're a human being, so we all make mistakes. So now the last digit is 1 times 2 raised to power 0. All right. Computer programming is not perfect. When you're even coding, you don't get it perfect. So we have 8 here plus this is 0 because anything times 0 is 0 plus this is 2 raised to power 1 is 2, then plus 2 plus 1. So this is correct. So maybe my mistake is from the positional. Sorry, my mistake. Oh my goodness, what's happening? Okay, wait, I don't press forward. Okay, sorry about that. Erase question. Yeah. Where did we get this from? Okay, all right, sorry about that. Okay, so I'm going to erase. Now, let us, it is that mistake that we are trying to sort out. Sorry, this video might be longer, but it's okay. All right. We make mistakes and we correct our mistakes. So I have been able to debug. This is basically an act of debugging. There is a mistake in my calculation. So I'm trying to find it out. So now let's go back. We will have 1, 0, 1, 1, 1. We have 0, 0, 1, 1. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. It's not supposed to be 9. It's not supposed to be 9. Really? It's not supposed to be up to 9. I think that is where the problem is. 2 divide 243 will give us 1, 2, 1. Okay, remember 1. Because 2 times 1, 2, 1 will give us 2, 4, 2. Give us 1. 2 go 30. 60 will give us 30. Oh my goodness. See the mistake here. See the mistake. All right. See the mistake. 2 go times 60 will give us 30, remainder 0. Okay, sorry. 2 go 243 will give us 2, 1, 2, 1, remainder. Okay, sorry. Oh, sorry about that. So maybe let me just use a shorter number to do this. We have seen 11, and 11 worked very fine. Okay, so maybe I don't want to take too much time because it seems I'm making some mistakes here. But the thing is, if you want to convert 11, something like 11 now, all right, to binary number, all right, you go and do your 2 go 11 will give you 5, all right, and remainder 1, 2 go 5 will give you 2, remainder 1. 2 go 2 will give you 0, remainder, sorry, will give you 1, remainder 0. So if you're trying it out, you can just help me and find out where my error is. 2 go 2 will give you 1, remainder 0. All right. Then 2 go 1 will give you 0, remainder 1. Okay. All right. Remainder 1. So in total, we are now having, we'll go from here up. So we have 1, 0, 1, 1. So this is 11. And when we convert this thing back to decimal number, we are going to get 11. We have done it severally here. Okay. So let me not waste time on this. Okay. So you divide repeatedly by 2, writing remainders in reverse. That's what we have just done. So if you convert 23 to binary, okay, let us also convert 23 and see what we get. I think I couldn't find where the error is coming from. Okay, I couldn't find where the error is coming from. So let us try 20. I think it's 23 that we have there. Let's try 23. We'll convert it, then we'll convert it to binary, and we'll convert it back to decimal. So we'll have 23. Okay. Then we divide by 2 and we'll get 22, we'll get 11 and the remainder will be 1. We'll divide 11 by 2, we'll get 5 and the remainder will be 1. We'll divide by 2 again, we'll get 2 and the remainder will be 1. We divide by 2, we get 0, we get 1 and the remainder will be 0. We divide by 2 again, we now get 0 and the remainder is 1. So here now we are having 5 bits. When we did 11, we got 4 bits. So we now have 1. If we go from down, we go in the reverse order, we go from bottom to up, we have 1, 0, 1, 1, 1. So if we were to convert this thing back to the decimal, let's go. This is the positional value 0, 1, 2, 3, and 4. Okay, so we have 5 bits here. So when we go, we'll have 1 times 2. Remember, the base is 2 raised to the power 4, which is 16, plus. There's no need. I'm going to skip this 0 because definitely 0 is going to be 0. Or I'm going to skip it because anything multiplied by 0 will give us 0. So that I just want us to be faster. So 1 times 2 raised to power, it will give us 1 times 2 raised to power 2, which is 4. So we have 16 plus 4 already is 20. Then plus 1 times 2 raised to power. Oh, sorry, this is raised to power 3. Oh, man. Sorry, okay. This is 4. We have skipped this 0, this position 3, because it's going to give us 0. And then the next one is raised to power 2. Then this one is raised to power 1 plus 1 times 1. Sorry, 1 times 2 raised to power 0. So we are going to get 8. Sorry, we are going to get 16. What's wrong with me? Oh my God. All right, so we are going to get 16 plus 2 raised to power. I'm correct. Yeah, 2 raised to power 4 is 16. 16 plus 4 plus 2 plus 1. So 16 plus 4 is 20. 20 plus 2, 22 plus 1, 23. So this is correct. So you can see somehow in the other one, I really made a mistake and I can't really find it out. Okay, maybe because of I'm still teaching. If I'm more calm or something, I would have sorted it out. But you can help me and do that. But you can see how we are doing this now. So just follow these steps, okay? All right. So you can convert decimal to binary. That's what we have done repeatedly, okay? And you can also convert decimal to octal. You have to do the same to divide by 2 by 8 repeatedly, okay? Let's take a look at, let's convert from decimal to octal. You just have to divide by 8 repeatedly. So I'm going to erase everything here. I think I'm enjoying this, my new board, all right? This is Microsoft Whiteboard, amazing. All right, so I'm going to, we had 57 base 8 the other time in our slide. Base 8. Oops. This is 8, sorry. We want to convert it to base 10. And then we got 47, remember. All right? We got 47 base 10. So let's convert. So we are going to divide this 57 repeatedly by 8. And we'll get the remainder. So 57 divided by 8. 56 will give us 7. Remainder words. 57 divided by 8. 57 divided by 8. Please let me get my calculator. My head is no longer functioning. Okay, so 57 divided by 8 will give us 7. All right. So come on. So we have 8 times 7 will give us 56. So we are going to get 1, remainder 1. And 8 goes 7 will give us 0, remainder 7. Is it 57 that we did the other time that we got? Okay, all right. So we divide from decimal to octa. Oh my God, I'm doing octa to decimal. That's wrong. I'm sorry. Okay, we are converting from decimal to octa. That's what we divide by 8. I'm so sorry, please. I'm so sorry. So we are what we are doing here is that we are converting from decimal to octa. So let's say we have 47. This is where we are supposed to do that. This is 47 base 10. All right, let's convert it to octa. So we are going to say 47 and we divide by 8 repeatedly. So 8 go 47. What are we going to get? 8 go 47. 40 is 5. Okay, so it is 5. Remainder what? Remainder 7. All right. All right, yes. So 8 go 5, it is 0, remainder 5. And what do? We go in reverse order. So this will now give us 5, what? 7. All right, but in base 8. So if you want to, now you can see how we divided repeatedly. 47 divided by 8 will give us 5, remainder 7. 5 divided by 8 will give us 0, remainder 5. So that's how we got 57 when we go upward. So if you want to convert from octa to decimal, you just have to multiply their what? You multiply their positions. So we are now converting 57 base 8. We want to convert it to decimal. So what do? This is position 0 and this is position 1. So we do 5, all right, times 8 raised to power 1 plus 7 times 8 raised to power 0. So 5 times 8 raised to power 1 is 8. 5 times 8 will give you 40. All right, plus 8 raised to power 0 will give you 1. 7 times 1 will give you 7. So when you do this, it's equal to 47 in base 10. All right, so that is basically it. That is basically it. Okay, so now let's take a look at converting from decimal to hexadecimal. All right, it's basically the same thing. Divide repeatedly by 16 and then go upward. All right, it's just basically the same thing. So how do you convert binary to octa? All right, binary to octa, when you have a binary number, you have to, if you want to convert it to octa, you will group them in 3 bits. You group them in 3 bits, all right, from right to left, and then you will convert each group to its octal equivalent. All right, you convert each bit to its octal equivalent. So example, we have 110, 1110. All right, so we are going to group them in 3. So we have 110 and 110. So this 110, you have to convert it to the decimal value and convert this one to decimal value. So the decimal value of 110 is actually 6. All right. and the other one is also 6. So you combine them, you get 66. Okay, so let me show you. So please, you need to understand these things, all right? Although when you're programming, you might not be using them, but there are cases where you might be using them, all right? So you need to understand this simple thing. So we are converting 1, 1, 0, 1, 1, 0, base 2, and we want to convert it to base 8, all right? So what do we, the first thing we do is to group them in three bits. So we'll say 1, 1, 0, and the next one is 1, 1, 0. So this is in base 2, all right? So we now have to convert each of them to base 10 so that we can get the digits for the octave. So 110 will give us, this is 0, this is 1, and this is 2. So I can just do it right away. 2 raised to power 2 is 4. All right. So I will say, because 1 times 4 will give us 4. So 2 raised to power 2 is 4, plus 2 raised to power 1 is 2. Okay. Plus 0, anything multiplied by 0 is actually 0. So we will leave it. So it will be 4 plus 2. This is also going to be 4 plus 2, which will give us 6. All right. Both of them will give us 6. So we'll now add 6. We'll now put the 2 6 together, and we'll get 6, 6 base 8. I hope you understand this. Okay. If you have understood what we have been doing so far, you're supposed to understand this one too. All right. So now we have converted it and we got it. So how do you convert from octa to binary? Okay, you convert each octa digits to 3-bit binary. Do you understand? So you convert 7. If you have 75, you convert this 7 to 3 bits. You convert this 7 to binary and convert 5 to binary, and then add the two of them together. I don't think I should do this one for you again, because if you understand what we are doing, we have 7, 5 base 8. You want to convert it to binary. All you have to do is to convert each digit here to their binary. You know how to convert from decimal to binary. I have shown you here. So do it yourself. Convert 7 to binary, convert 5 to binary, and then put all the digits together, and you get the base 2. All right. So that is how it goes. You can even try and convert it back to see if you actually got it. Okay, so the same thing with binary to hexadecimal. Now, instead of grouping them in 3 bits, you group them in 4 bits. When you want to convert from binary to octa, you group the binary digits in 3s. But if you want to convert from binary to hexadecimal, you group them in 4 bits. All right, so when we have something like this, you group them in 4 bits, convert each of the 4 bits to their decimal value, and then when you convert and you have anything more than 9, remember, the hexadecimal starts from 0 through 9, then A, B, C, D to F. So if you get anything like 0, if you get anything like 10, know that it is going to be A. If you get anything like 11, know that it's going to be B. 12 will be C, D will be 13, 14 will be E, and 15 will be F. Okay? Now, I want you to do this yourself. Okay? And if you don't get it, please reach out. Reach out to us. I want you to do this thing yourself. I want you to work this thing out yourself. Now, we have grouped them into four bits. We have this group for 4 bits. Then we are going to convert each of these 4 bits to their decimal. All right. And you can see it seems like 1011 is B. What is B? B is 12. Sorry, B is 11. Okay. So, and remember, 1011 is 11. Remember. But since we are not dealing with decimal, 11 is B in hexadecimal. So I want you to do this yourself. If you don't get it, you reach out. All right? Do it yourself. And the result is BE on that 16 base 16. Okay? So you can also convert each hexadecimal digit into 4-bit binary. So if you have a hexadecimal value like this, 3 and C, first of all, you convert the 3 into 4 bits binary. You know how to do that. Then this C, you're going to, you cannot convert C to binary, what you have to do is that what is the decimal value of C? Decimal value of C is 12, right? So we now convert 12 to binary. So you can see, all right, C here is 1100 because C is 12. Decimal value of C is 12, and you convert that 12 to binary, you get this. I'm intentionally leaving this thing for you to do. I want you to rack your brain, all right? And if you don't get it, please reach out to me, all right? So thank you very much. Do your assignment, write your test, and I'll see you in the next class.